The cell potential. The cell potential measured by using the voltmeter. In reality, we can use our multimeter that comes with the kit to measure the voltage. Cell potential measured in volts, electrical volts. And the measured voltage, it depends on the difference in the capability, the difference in the capability to give up electrons. The cell voltage can be easily measured with a multimeter. I'll show you. I have a very simple multimeter. Oops. It's not really designed for copper penny, paper towel. I make the paper towel wet with the tap water. I use tap water just because tap water contains ions. So that makes the tap water conductive to electricity. And the other end use a copper foil, the tin foil that I use for packaged food. And so that's the very basic voltaic cell. So compared with the normal voltaic cell we see from the diagram, the wet paper towel, it is acts as a salt bridge because it has a non-active, non-reactive ions. And I measure voltage between these two. The voltage between the aluminum foil and copper penny, it shows you the difference in the metal, which metal is easy to give away electrons than the others. And so this is a multimeter I turn on. The reading should show the zero. Show zero. Okay. And the aluminum foil is fairly reactive. It's very reactive. Okay. Aluminum more reactive than the copper. So the aluminum metal should lose electrons. Copper metal is where electrons will flow into. And if you touch these two, it will give us a reading. You can see the reading is 0.6, 0.61, around 0.6. And the reading is positive. That shows the electrons moving out of aluminum foil into the black electrode. And the electron finally move to into the copper. If I switch these two, the red with aluminum foil, copper with a black probe. You can see the reading is negative, essentially the same reading as you've seen before. It should be the same reading. The reading keeps fluctuating, so but it's roughly the same value except negative reading. So this is a proof that the electrons moving out of aluminum foil and moving back towards copper. And the chemical reactions, it depends on the tiny amount of ions in the tap water versus in the paper towel. That is completed redox half reactions. So that's how you measure the cell potential. And I showed you earlier in the before the class. With the AA batteries, you can do the same. For the AA batteries, a little stud, this is where the positive end of the battery. So put that with the red. And the negative end is the flat part of the battery is flat. That's negative. You do that, you have reading 1.55 volts. That means the battery is essentially a fresh battery. Okay. So in this alkaline battery, this this is cathode reaction, which is reduction half. And electrons coming from the flat bottom. So the flat bottom, it is the anode reaction, oxidation reaction. Later we'll get into the what is made of alkaline batteries. It is essentially zinc mixed with some other electrolyte and made into layers. Among the layers, there are layers for salt bridge, layers for the electrolyte that is going to react. And all these combined together give us a voltaic cell. That is, we measure the voltage for that. The cell measure the voltage being positive. That means the reaction is spontaneous. The standard cell potential, the E naught, you see this E naught, not again, E0, which means the gas, if any gas involved in the reaction, the partial pressure of the gas is 1 atmosphere. And if there's a solution involved in the reaction, the solution has different molarities. A different concentration will cause a difference in the ions giving or taking electrons. And so we specify the standard state for the solution. It is a 1 molar, 1M solution. And so this is how you measure the standard cell potential between the copper and zinc half. And these are the salt bridge. The solution is 1 molar exactly. Both solutions 1 molar. The measure the voltage is the standard cell potential. It shows the have no current, no electric current. Because when the electrons flowing, once the electron flowing, the resistance will cause a change in the reading, will become lower. That voltage, it is a working voltage. It's a voltage under load. It's different from the voltage without electron flowing. This voltage is essentially the highest voltage reading you can have between these two, because under load, once you use the battery, voltage will drop. And so that's the standard cell potential we measure with a standard concentration. So these are some examples of the voltage we'll measure in life, in nature. The common alkaline batteries, the voltage is 1.5. Fresh battery oftentimes 1.6 volts. So now everyone has the voltmeter that you come with a kit. Keep that. The multimeter you have in your kit in the future will use in many, many occasions. So for example, you have battery, you want to check the battery is good or bad. If the alkaline battery, AA, AAA, or size D battery, the voltage from fresh, it should be 1.6 volts. That's for fresh, completely unused. Typically, if the voltage below 1.2 volts, that means the battery is dead. You just throw it, throw in the electronic waste. And actually, I accumulate a whole bunch of electronic waste because the electronic parts, cheap, they don't last. They need to be specially disposed of, not the regular recyclable trash. So that's the alkaline battery, AA, AAA, size D batteries. The car has a lead acid battery. This battery, each one cell is about 1.2 volts. Freshly charged battery, I think, can go about 2.2 volts per cell. In the car, the batteries is linked together in series. So that means one battery, you got a positive, negative one. You link with the other battery, second battery, and in the same direction. But the anode of the first battery connected with the cathode of the second battery. And for the second battery, this anode linked with another third battery cathode. So it's almost like all the snakes bite on each other's tail and form a full circle. That is we call in series, connection in series. The final voltage simply just adds up. 2.2 or 2.1 volts times 6 give you 12 volts. And the calculated battery is about 1.3 volts. They are different. Lithium battery, the 3.7 volts, it is actually the lithium ion. For lithium ion batteries, 3.7 is about 80% of the capacity, roughly 80% or 50% capacity. The fully charged is about 4 volts, if I remember correctly, 4 volts. That's fully charged. The lithium-based battery, either lithium ion or lithium polymer batteries. These are batteries used in the Tesla car and our many newer electronic power, like electric mower, electric vacuum. These are used lithium batteries, fully charged about 4.0 volts. The very important for those lithium-based batteries, you charge only right before you use them. Do not charge to full every time once you finish use them. Because the lithium, once you restore into the reactant form, is more reactive and is more vulnerable, can react through the leak. It reacts. Over time, the quality will deteriorate. And the capacity will have a significant decrease if you maintain your battery fully charged without using in storage. So in storage, very important, you should make your batteries halfway depleted for storage. Okay. So basically, you can make your cell phone battery last longer by avoid stay at 100% charge the whole time. If you don't use battery overnight, ideally the 50% capacity. Your battery shows you 50% capacity. That's the ideal for long-term storage. If your battery drained to below red, which is very low, which is about very close to 3.6 volts, that's damaging for the battery too. So the lithium battery, the key is absolutely avoid high voltage, full charge without using. And also avoid the too low voltage for too long. That's damaging for the battery too. So it's kind of picky. There are many other batteries in the market, much more less maintenance than the lithium ion. But lithium ion's battery is very lightweight, high power, has so many advantages. The key is to maintain healthy by avoid too low voltage or too high voltage. It's similar to a person. As a person, every time when a person eats, it should be, first of all, absolutely avoid overeat. Overeat is very damaging for health, for whatever reason, so many reasons. And also, you should avoid being too hungry for too long time. And that's just like a lithium battery. You should avoid both ends. And actually, there's a research completely beyond the point, is the experiment on the rat. The rat maintained at half full, live much longer than the rat that is always 100% full the whole time. And it's good for the animal's lifespan, the longevity. So same as for the battery, because battery is not too cheap. So if you want to make a battery last longer time, just to maintain half if you don't use it. And if you charge the full, use as soon as you can. Do not leave for too long. Batteries in living organisms, the electric eel, the fish in the ocean that is have many 5,000 electric cells in the body. those cells, each cell has about 0.15 volts. It's not very high, very low voltage. It is much higher than the voltage between my two hands. Those of you who watched me earlier before the class, I showed you there's a voltage between my two hands. It's about 0.05 volts. The electric cell in the electric eel, it has about 0.15 volts. Those 0.15 volts in 5,000 cells, all the cells in connection in series, just like this, the voltage will add up to about 750 volts. 750 volts, even the amps, the current not very high, it can give a serious electric shock to most living organisms. If a human goes through the 750 volts, that's a very high voltage shock. It'll be very similar to the taser gun effect. Basically, the animals, marine animals, small animals being electric shocked by the electric eel, it can be used for defense or for preying, or basically knock out the potential food. Nerves, giant squeeze the voltage. It's just about the voltage between my two hands. That's very tiny voltage. The nervous system in human and I believe many living organisms is based on electrochemical reactions. There's a 1/2 reaction we use as a standard. It is the use of hydrogen electrode. Standard hydrogen electrode as a She. We use a hydrogen gas and a inactive electrode, which is a platinum. And this platinum is especially treated. It's porous, and so it's highly catalytic. It helps the catalyze the reaction between the hydrogen gas and hydrogen ions. So this reaction, when the hydrogen ion gain electrons, becomes hydrogen gas and maintain the ion concentration as 1 molar gas pressure as 1 atmosphere, the voltage we define as designate as 0 volts. It's treated standard. It's a standard cell. So when we link this half cell with the other half cell reactions, we can measure voltage. And that voltage, it will be the voltage for the other cells. And so we treat the hydrogen cell as a standard. Very similar to the enthalpy formation. Enthalpy formation for the most stable form of elements are designated as 0 kilojoule per mole. And in a very similar way, we define the hydrogen electrode as 0 volts as a standard. The standard cell potential is based on the cathode and anode reaction, the difference, the voltage difference between these two. The voltage difference between these two will give us the standard cell potential. Very important, the cathode anode, especially the solution or gas, it has to be the standard states, which means 1 molar concentration for solution, 1 atmosphere for the partial pressure of the gas. So when you have those standard conditions, these values are given in the table. The difference between these two values will give us the cell potential. We call it standard cell potential. We can measure those with the voltmeter that I have between the standard cell, 2 half cells. And if I use one of the electrode as hydrogen, the She, the standard hydrogen electrode, the measured voltage will give us as the standard reduction potential. This is called standard reduction potential. SRP, standard reduction potential. The standard reduction potential nowadays, since it's measured on the standard condition, the 1 molar concentration, It has been tabulated as a standard thermodynamic data. And then we can check and use that for predicting the redox reactions, if the redox reaction be spontaneous or not. Those EX are the different half-cell reduction potentials. How to find those reduction potentials? We link those, the target half-cell reaction with the standard half-cell reaction, the hydrogen half-cell reaction, and measure the voltage. And since the standard hydrogen cell voltage designated as 0, the measured voltage will equal to the standard reduction potential of that target half reaction. So measure voltage between the target, the unknown half reaction, as against in conjunction with the hydrogen, the C. That voltage is defined as the standard reduction potential. This value we can find from the thermodynamic data or the reduction potential data table, data sheet. And this can be used as a measure of the oxidizing power of the oxidizing agent or reduction power for the reducing agent. And so this is the value we use, and we can have a table for that. So how to set up the unknown cell with the C standard hydrogen electrode? It is when you have a targeted reaction. This is target half reaction. And this is a standard hydrogen sheet. Linked together, we measure voltage. Measure voltage is give me the value, and combined with the direction of electron flow, we finally decide the zinc half cell potential will be negative 0.76 volts. Negative 0.76 volts. So that'll be the half cell reduction potential for zinc half reaction. Link these two together and measure voltage. We get the zinc cell standard reduction potential. And so here is how the chemists been measured all different systems. This table, this sheet is not complete. We have a much longer sheet. It will be given in the exams in the past. You might have seen the past, or you can see on the information sheet given for the final exam. You have a much bigger sheet for that. So that sheet shows you the voltage reading in conjunction with the hydrogen standard electrode, measured voltage. You can see the fluorine gas gain electrons become fluoride, has a very big positive potential. And you can see the lithium ion to gain electron become lithium metal. The reading is a very, very large negative value. Each has a specific meaning for that. Very specific meaning for that. Very positive value, it means the reactant is a very strong oxidizing agent when you see a big positive voltage. And being negative, which means the reactant is not a good oxidizing agent. Instead, the product, you know the product. This product is very strong reducing agent. That's when you see the negative voltage. So positive voltage, you look at the reactant as a strong oxidizing agent. And negative voltage reading means the product is a very strong reducing agent. And with the standard reduction half reaction, we can find if you have an unknown, what is the reduction half reaction for the unknown half reactions? based on the given cell measurement. So this is an example how we use the standard cell calculations to find the cathode anode reactions. This is how Voltaic cell have reaction between the aqueous bromine and zinc metal. It's built as a Voltaic cell, so the reaction will be carried out into two half cells. One is the reduction half, the other oxidation half. And this is the overall reaction. Okay, very, very important. Pay attention to the overall reaction. The overall reaction shows you which one's been reduced, which one's been oxidized. Okay, and we measure this cell potential is 1.83 volts. This is overall cell potential. And you are given the bromine, you're given the zinc. Zinc potential is negative 0.76 volts. You know the zinc. And this cell has both bromine and zinc. You are given the zinc. Let's find out how much is the bromine. And so to find the bromine cell potential, and we know the overall cell voltage. So remember the cell voltage, we use the cathode minus anode. With cathode minus anode. And the difference between these two should give us the cell voltage. Well, with this overall reaction, how do we know which one's zinc? Cathode anode, which one's zinc? Which one's bromine? If you know, then the problem will be very easy to solve. Let's say if I know this is the zinc, then to find the anode, which is bromine, you simply just rearrange and subtract. You find the anode. Or if you know this is zinc, then the cathode will also very easy to solve as well. Just adding the volt. Anyway, we need to know which is which. So keep in mind the cathode is the reduction half. Cathode is a reduction half, is red. And anode is oxidation, redox. So the red ox separate. And you look this reaction, bromine Br2 with zinc metal give you zinc ion. How do you know which one is reduction, which is oxidation? You can break down the whole reaction into two half reactions, the bromine half and zinc half. And if you do that, actually you can see fairly quickly see which one's reduction, which one's oxidation. The bromine half will look like this before it balance. And you can see the use oxygen states. That really helps you decide which one reduced, which one's been oxidized. This is the element. So bromine oxygen state 0. And the bromide ion, the oxygen state is -1, same as charge. So you can see the bromine from 0 becomes negative. The bromine oxygen number decreases. For the bromine, oxygen number decrease, which means it is reduction. Because oxygen reduction is decrease in the oxygen number or decrease in the charge because of gaining electrons. Okay, so by doing this, break down the two half reactions, we can decide which elements is being reduced. And then we know that reaction, since the bromine reaction is reduction, it is the cathode reaction. The bromine is cathode reaction. What about zinc reaction, zinc half reaction? If one of the half reaction you decide is one of the two, reduction oxidation, then the other half reaction will be the opposite. The bromine reaction here we decide is reduction. So the zinc must be the oxidation. And so just we verify that zinc, you can see from the zinc metal become zinc ions. You look at the oxygen numbers. Oxygen number for zinc, this is the element, will be 0. And this is zinc cations plus 2. And you can see the oxygen number increases. That's a sign of oxidation. Oxygen number increase, that's because it is oxidation. It's oxidation reaction. So once you set this down, the bromine is a reduction, which means the cathode. Zinc, of course, will be the anode because the oxygen number increase is oxidation reaction. Then we can rework on the formula that we have in the beginning. Okay, the cell potential, it is 1.83 volts. That should be the cathode half reaction. As we decided, cathode half reaction is a bromine. It should be the bromine half cell voltage minus the anode, which is zinc, as we decided. The anode is oxidation reaction. So this will be the zinc. And once you decide this, the rest will be fairly easy. The bromine is one we don't know. We do not know. The zinc value is negative 0.676 volts. And then you can easily solve the bromine. The bromine should be 1.83. This part becomes positive plus 0.76. You subtract 0.76 on both sides of the equation. Then you will get the bromine voltage, which is 1.07 volts. And it's positive value. So this is how you find the cell half cell reaction voltage if you know the overall reaction. And you are also given one of the half cell, the other half cell voltage. This standard reduction potential for zinc is given in the table as we see in the earlier, a moment ago. So that's how you find out the bromine, an unknown half reaction. So what does this standard reduction potential mean from the table? The cell potential standard value, which means gas has partial pressure of 1 atmosphere, and the solution concentration, it should be 1 molar. That standard cell potential, it gives us a comparison among the reactants and products. Among those reduction half reactions, okay, this is the reaction. Each one, the standard reduction table we've seen earlier. Let's quickly go back to that page. There's a table. This is a table. It shows you have the all the reactions are the reduction. Okay, all the reactions are reduction. You can see the electrons on the right-hand side. Those electrons all in the right-hand side. Okay. So each reaction is a reduction half. Remember the oxidation half reaction, what we just flip, reverse each of the reactions will give us oxidation. This table only compares the reduction half. Okay, only compares the reduction half. So with all the reduction half, the higher, more positive voltage value, more positive, means reactant. How good, how well it acts like oxidizing agent. Because oxidizing agent goes through reduction reactions. It's a reduction reaction, and the oxidizing agent being reduced. Oxidizing agent being reduced. The more positive value for those half cell, it means the more readily, more easily for the reactant act as oxidizing agent. And so pay attention to the reactant. More positive means the reactant easy to gain electrons. So as you can see from the table, fluorine gas, gain electron become fluoride. Voltage is positive 2.87 volts. It's a very big positive. Means fluorine gas is the strongest oxidizing agent. So there's a little bit of history about the discovery of halogens. The halogens including fluorine, chlorine, bromine, iodine. These four are the most common halogens. And among the four halogens, iodine is easiest to obtain. You can use some fairly weak oxidizing agent to oxidize iodide, become iodine. So very easy. Bromine is a little hard. Br2 is a liquid, pure reddish brown liquid. You need a stronger oxidizing agent to get that. Chlorine gas is much harder to get. In the industry, we use electrolysis. We force the chloride ion to give away electrons, so the chloride becomes chlorine. Fluorine gas is the hardest to obtain because fluorine gas is the most reactive gas among anything. It's the most reactive gas. It reacts with literally anything is in contact with. So the fluorine gas to obtain, we need a very, very strong high voltage electricity to force electrons out of fluoride ion. Okay, we force the electrons out of fluoride ion to become fluorine gas. So this shows you how reactive, how powerful the fluorine gas as a reagent, because the very high voltage, which means it's very, very easy for those reactants gain electrons, become product. So that's with positive, very large positive reduction potential we see from the table. What about negative? Okay, the negative. This is an example of negative. Lithium ion gain electrons become lithium metal, the voltage is -3 point. This means lithium ion is very, very difficult to gain electrons, become lithium metal, which also means the opposite will be true. It'll be very easy for the lithium metal to lose electrons, become lithium ions. So in that table, in the same reduction potential table, the negative, very large negative voltage, it means for the product, it's very easy for the product to lose electrons. Since lose electrons, it acts like a reducing agent. Lithium ion, lithium metal in the aqueous solution, it is the strongest reducing agent based on the most negative value you see from the table. So when you see the negative, means the product very easy to lose electrons, give you a stronger reducing agent. A moment ago, we saw the zinc. The zinc cell potential is negative 0.76 volts. And that means zinc metal is a fairly strong reducing agent. The copper cell voltage, copper 2 ion, that voltage positive 0.34 volts. So that means the copper ion, copper 2 plus ion, is a very mild oxidizing agent for them to gain electrons. So that's the relative magnitude of those standard cell potential in the table. So to summarize, those are the highest, most positive values, which means those are strong oxidizing agent. Fluorine gas, chlorine gas, and manganese 4 oxide. So these are very strong oxidizing agents. And those with very negative values, big negative values, means the product are the strong reducing agent. Okay, so in this chapter, we learn about the definition of cathode, anode, how to calculate the cell potential. And if you recall the last chapter, we spent time on discuss the entropy change, enthalpy change, and temperature, how they work together. It helps us decide if the reaction, forward reaction is spontaneous or not. In this chapter, we will not be using the entropy or enthalpy. Instead, we'll be using the standard reduction potential as a tool to predict if the redox reaction be spontaneous. So use that table we saw before. In reality, you will be given a much bigger table, has more complete set of reduction potentials to use. So let's say we have a generic reaction like this. A1 with B1 becomes A2 and B2. The A becomes A1 becomes A2. B1 becomes B2. So this will be the half reaction. How we decide the reaction spontaneous or not? Let's break it down into two half reactions. And then with these two half reactions, identify is a reduction half or oxidation half reactions. To find out a reduction half or oxidation half, there are two ways. One way it is to balance the half reactions, both half reactions. And we learned from the last week, balance with half reaction. And there's a much easier way if you're familiar with oxidation numbers. Observe the change in the oxidation numbers. So the two ways. If you use half reaction, balanced half reaction, how do you know the reduction reaction? Is when you see the electrons as a reactant. That half reaction will be the reduction half. The oxidation half is where the electrons behave like a product. So reduction half is electrons needed for the reaction. So electrons to bring down the oxidation number. And oxidation half, oxidation number increases. Okay, so that's how you know the reduction and oxidation half. Here shows only if you use the half reaction, how they know reduction and oxidation. And now that we change oxidation numbers, when you see the oxidation number from left to right, it increases. That means the oxidation half. If from left to right, from reactant become product, that half reaction, the oxidation number decrease, and that will be the reduction half. So either way, I would recommend you do the oxidation number because that's the quickest way. Balanced half reaction is good practice, but takes longer time. So once you decide which half is the reduction, the other one is oxidation. Then we use a table. So this part you use a table to find out those values. Find out values corresponding to these two half reactions from the table. Or the question might give you the information, give you the half cell voltage, which is based on the same table. So how do you find those reactions in the table? There's a little bit tricky if you try to look for the oxidation half. Okay. Reduction half, you should find the easy match in the table because the table is the list of reduction half reactions. So to find a reduction half, it is easy. However, if you try to look for oxidation half reaction in the same standard reduction potential table, you will need to reverse. You will need to reverse the oxidation reaction. Then you look for the match. Because that whole table is about reduction reaction, which is the reverse of the oxidation. So for this reaction, when you look for the oxidation half and the voltage for that reaction, you'll need to reverse that, and then you look for the match. So we'll see all these in the example. Once you're done, find out the values for both the reduction and oxidation. You calculate the cell voltage for that given or the target reaction. Use cathode, which is reduction half voltage, from the table. Subtract oxidation voltage you find from the table. Okay. If the difference between these two is a positive, then the reduction reaction will be spontaneous. So this is how you determine the given you a reaction, redox reaction, and let it predict if the reaction is spontaneous. It has several steps. So the key is to identify which one is the reduction half, and the others will be the oxidation. And the oxidation half, look for the voltage. You need to reverse the oxidation half, and then look for the number from the table. So let's see a real example. I have two examples for how to predict redox reaction, spontaneity. So the first example, will the permanganate ion oxidize chloride ion to form chlorine gas and manganese 2 ions? This question asks you, can this oxidize that? Which means you can write down the reaction for this and predict if this reaction be spontaneous. So this word problem we need to translate into the reaction first. Basically, you write down the chemical formula, an equation based on this. Will permanganate ion oxidize chloride ion? So these two should be the reactant. Permanganate and chloride being the reactant. So basically, we are to predict if this reaction is spontaneous. And then we have the product. The product shows you is the first chlorine gas and the manganese 2. So you have two products. You have chlorine gas and a manganese 2. The question now becomes, can this reaction be spontaneous? Or in other words, we need to find out if this is true. If this is true. And so this is the reaction, and we should follow the steps in the previous slides. First, break down into two half reactions. The two half reactions, we have permanganate. That should give me the manganese 2 ions. And the other half is chloride, becomes chlorine gas. So that's the two half reactions. And then which one's reduction half? Which one's oxidation half? One way, the first way I mentioned in the previous slide, it is about balance two half reactions and find out where electrons located. Electrons in the left in the final balance equation. That means the reduction half. Electrons on the right, it means oxidation half. So that's one way. That takes longer time. And the easier way, it is do the oxidation states. The balance equation, we did this reaction before. I will not do that here. We don't have time to do that here. But let's use the oxidation states. It's just much easier, and that's why we have practice on those. If you use oxidation states for permanganate, we decided oxygen first, -2 first, and then the manganese here will be +7. So that's the oxidation states in the two elements in the permanganate ion. And then the manganese 2, the single monatomic ion. So the oxygen number is same as charge, +2. So these are the oxidation states. And the oxygen, we normally do not look at it because in the product, there's no oxygen as a product. So we don't look at oxygen. By default, oxygen and hydrogen normally will not change unless hydrogen changes form. And here we don't have hydrogen, and oxygen is missing in half reaction. We do not look at oxygen. And then the rest will be easy to see. The manganese from +7 becomes +2. The question is this a reduction half or oxidation half, and why? From permanganate to manganese 2, is this a reaction reduction half or oxidation half? Can anyone chime in?
Oxidation.
Oxidation, it should be the oxidation number increases. So let's quickly refresh. Oxidation number increase, that's the oxidation reaction. Oxidation number decrease, that's a reduction. So you can look at the manganese here. What happened to manganese? Does oxidation number increase or decrease? From +7 become +2. The manganese have a decrease in oxidation number. So the manganese should be reduction. This is reduction half. Because you have decreased by 5, which basically means each manganese atom gained 5 electrons. So the oxidation state becomes from +7 become +2. Is a reduction for manganese. Manganese is being reduced. Yeah, look at the oxidation number change and how they change. Decrease means that element being reduced, and increase means element being oxidized. Any questions about this? Use oxygen number change to help decide. The other way might have been easier for you, it's just longer work, is a balanced half reaction. Use the water, proton, electrons to balance. You'll see the same results. You will see the 5 electrons is needed, and you add all the water and the protons to complete balance equation. You will need 5 electrons in the reactant. And that's shows you the it's been reduced for the manganese. Okay, if this half you verify it, you're very confident the reaction is reduction, then the half, there's no need to look at it. It should be the oxidation half. But just to be sure, let's do that. Let's find out the oxidation states. The chloride, what is the oxidation state for chloride ion? Can anyone chime in? Seems like we need some little review on this. What is the -1? -1, correct. Because it is a monatomic ion. Only one atom in this ion, and the ion has -1 charge, so that is -1. And the chlorine CO2, this is the element, so 0. And as you can see, the chlorine oxygen state from -1 becomes 0, that's an increase. Oxygen state increases. Increase, it means it's oxidation reaction. So this is a reaction, 2 half reactions. And if one half reaction you decide is reduction, then the other half should be oxidation, and vice versa. And chlorine is being oxidized in this half reaction. Okay, still, how do we know this reaction being spontaneous? Now we can start from here. We decide the permanganate reduction. Chloride reaction is oxidation. We need to find those reduction half cell voltages. This should be able to find from the table. And keep in mind, reduction is a cathode. I write down cat, it's the same means cathode. The oxidation half will be the anode. So you just need to remember one. Reduction is cathode. So this will be the cathode. Manganese, permanganate will be the cathode reaction. Chloride reaction will be the anode reaction. Cathode reduction, anode oxidation. And the next step, we find those values. Those values, I remember putting the PowerPoint. There it is. Okay. The permanganate is easy to look for. You basically look for in the table. If you see the permanganate ion in the reactant, then you find it. Make sure the reactant has permanganate, manganese 2 as a product in the same reaction. And this is value you find from the table. So from that table, you'll be given, or you'll be given the cell voltage. So the cathode is easy to find a match because reactant, you should find a matching reactant in the table. And what about the anode, the oxidation half? Where do we find this value? Okay, so this is a little bit tricky. The reaction we decide it is the oxidation half. So that means to find a match from the table, from the previous slides, let's go back to the table. To find a match from this table, remember this is reaction, all are reduction half. They are all reduction reactions. So you look for match in the oxidation, you will need to reverse that reaction. Reverse this reaction. So find a match. We need to reverse this reaction. This reaction, you cannot find a match from those half reactions because it's oxidation half. So we need to reverse this reaction. And then look for search the table. From chlorine gas become chloride. So reverse and search find the match. Reverse and match. There it is. It is actually fairly high up. And the voltage is positive 1.36 volts. And so anyway, for convenience, I already put in here. But this is how you should look for it. So basically the oxidation half, you need to reverse and find a match. And then I get these two half cell, the reduction potential ready for my final evaluation. Will this reaction be spontaneous or not? I'm based on these two data. So next, eventually I can, once I have a two half cell voltage, I can decide if this cell voltage, the entire cell voltage, positive or negative, then I will know the reaction will be spontaneous. After the breakdown two half reactions, decide which one is cathode, anode, find the match. Okay, this one's a little tricky, but find the match. And finally, I can decide. Okay. The cell voltage, which is indicator for the redox reaction, spontaneity. This is basically an indicator for the spontaneity for the redox reaction. You should use the cathode or reduction half. Cathode or reduction, same thing. Cathode reduction minus the anode. Anode or N. Okay, so cathode, we just decided based on the oxidation number or the location of electrons in the equation. This is a cathode. This is cathode. Permanganate is cathode reaction. And chloride to chlorine, this reaction. It is anode reaction. Cathode is permanganate. And anode, it is a chloride. Is oxidation half. So use the reduction half minus oxidation half. Permanganate value is 1.51. And the chloride anode reaction voltage is 1.36 volts. You simply subtract. And after this, what you get, it is a positive value. Since this is positive value, the reaction should be spontaneous. Yeah, the reaction is spontaneous. The answer is yes, spontaneous. Because in the end, you get a positive value. So there's a lot of work involved in the simple question like this. Break it down and identify cathode anode reaction, and then find the match and search for the data and do a final, use a cathode minus anode, or use a reduction half minus oxidation half. If you get a positive, then the reaction be spontaneous. It looks like take many steps, but do some practice. It's fairly quickly, easy to master. for this chapter, produce the spontaneity of a redox reaction. It is the central piece. It is essential in this chapter. There are some other quantitative calculations, use some equation, are relatively simple. So qualitatively use the standard reduction potential, predict spontaneity of redox reactions. It is the most important part in this chapter. We'll take a look at the next example. The next example will follow the similar steps. So the next example, I'll do more interactive. Okay. The second example is asked about which metal can reduce. Previous question focused on can that oxidize. This asks about reduce. It looks like I use the just opposite word when making questions. The nature of the question is essentially the same. It is to predict the spontaneity of those redox reactions.
Excuse me.
Yes.
Professor,
Yeah.
on previous question, how you found Mn, manganese 151?
This table, the I just realized this number is not in that table, but keep in mind the table we have in our lecture is very incomplete, very short. This table, this data come from a other source.
Oh, right.
But yeah, you should be able to find from the table, because in the quiz exam, I will give you a much bigger table. You can find all the reduction potentials you need for answering questions.
In the table that we have, it's plus 1.23. It's not right?
That's different reaction. It's good you bring this up. This is a completely different reaction.
Oh, okay.
Yeah. This is start from the manganese 4 oxide.
All right.
It's not the same reaction as we have. Yeah.
That's true.
I don't have the this number is very common value, but it's not included in our slides.
Okay.
It's in a different source. Yeah.
Okay, thank you.
Yeah, you're welcome. So, which metal can reduce iron 2 ion in aqueous solutions? And the metal you be given are the, these are the 3 metals we have. Copper, zinc, and aluminum metals, these 3 metals. And the values for the reduction half is given. There are many questions in the test, in the quiz. Reduction half potential has been given. If it's not given in the table, it should be given. And these 3 metals will ask which of the 3 metals can reduce iron 2 ion in aqueous solutions. The question's nature is very similar to the last question. These 3 are the common metals we can see in everyday life. Which of those 3 metals can reduce iron 2 ions in the solution? And so the reaction in general, we can write down the generic reaction looks like this. Sorry, so the bottom slide. This is generic reaction. And metal, okay, metal becomes metal, iron metal, and the metal becomes a metal ion, and that'll be the generic equation. It's unbalanced. You can easily balance that if you're interested. Can this reaction be spontaneous? So follow the same route. We divide into 2 half reactions. you have a metal become iron 2+ ion becomes iron metal. And the metal N becomes metal cation. So break down into 2 half reactions. In the 2 half reactions, and then use oxidation states to decide which half reaction is a reduction. And the other half reaction, it should be the oxidation half. And you can see the iron. I have a question for you guys. Is iron being reduced or being oxidized in this half reaction? Is iron being reduced or being oxidized? What is the oxidation number for the iron? So here is +2. What about the oxidation number in the iron, the Fe? It should be 0. Did I hear 0? I hear someone say 0. 0. So the oxidation state, iron here is 2, and iron becomes metal 0. There's the oxidation number decrease. That's a reduction. And also, by the way, when you write an equation like this, the question, it also mentioned the iron should be reduced. So of course, iron should be the reduction, which means the other one will be the oxidation reduction. You can also use the compare oxidation numbers. This is the metal elements, 0. And here you got a positive N as a charge. That's the oxidation number. There's an increase, so that's oxidation half. So the iron's reduction, the metals oxidation, you find a match. You find from the standard reduction potential. Here, this question, I already give you those numbers, so I don't have to flip back and forth, check the table. The reduction, this is the reduction, this is the metal oxidation numbers, all here. Next, let's calculate the cell potential. The cell potential calculation, remember, use a cathode, which is reduction, minus anode, oxidation. The reductions is iron. Here is iron. And the other metal is oxidation reaction. It's anode. So put it here. It is basically the iron reduction potential minus any other metal, whatever unknown metal, their reduction potential. If the difference between these two, which is cell potential being positive, then this reaction will be spontaneous. Okay, let's see. Okay, let's see. Here, it basically means, if you translate, that means the iron reduction potential should be larger than the metal reduction potential. And we have 3 different metals to choose from. So we compare them one by one. Whichever compares the iron is smaller. This is the iron value. The metal with a lower reduction potential than iron should be able to reduce iron. And we have the first copper. Let's look at one by one. The copper is larger than iron, so this is no. This metal, it is actually larger than the iron reduction. So this copper will not reduce iron. But look at zinc. Zinc value is less than iron. So this is yes. And aluminum, oh, there's a mistake in my aluminum. This number is actually, sorry, this is a big typo in here. This aluminum value is not the 0.44. If you check online, I need to correct this. Check online. check from my textbook, it should be about 1.66 volts. This number is off. The reduction potential value you can find from the textbook in the appendix, among the appendix. Okay, appendix give me the reduction potential for aluminum. What I find from my table, it is a negative 1.66. This is a big negative 1.66. So you can see the aluminum with the reduction potential is negative 1.66. That is smaller than iron. So this one's a yes. You should be able to reduce the iron. And so the answers for reducing the iron 2 plus ion among the common metals, aluminum, copper, and zinc, aluminum and zinc can reduce iron 2 ion, and the copper cannot. Copper cannot reduce iron 2 ion. These two metals can reduce the iron. Can reduce iron 2 ion. And so that's how we use the standard reduction potential to predict if a redox reaction be spontaneous, or in other words, can this reduce some other reagents, or can that oxidize other agents? It all translate or boil down to predict the specific redox reactions be spontaneous or not. And so that's how we predict the reaction